Okay, so just a few recall about what we've seen so far. So this m star beta, we have defined it in several ways, but well, it's equal to the magnetization at 0 for the plus Gibbs state, so the Gibbs state which is obtained taking the limit well, with infinite boxes with plus boundary condition, okay, with size of the boxes tending to infinity with plus boundary condition. Okay, I will just start now to erase the dependence in H, okay, as H will always be equal to 0 in all this class. And okay, this thing was also defined as the right derivative of the free energy at H equal to 0. So what we have seen so far is that m star beta is non-decreasing, okay, as a function of beta. We've seen, so this was two lectures ago. We've seen in the last lecture that when beta goes to infinity, the magnetization tends to 1. So in particular, m star of beta is positive for beta large. Okay, and basically the last step we need to prove that there is a phase transition for this quantity is to prove what we are going to prove today, is that m star beta is equal to 0 for beta small. Okay, so if you remember, to treat the case of large beta, what we did is we took a different view on spin configurations. So we looked at the set of edges on the dual lattice that separated plus spins from minus spins. Okay, and we saw that this collection of edges, it formed a family of contours. And yeah, basically we studied like the Ising measure, but not as a law on spin configuration, but as a law on families of contour in order to say something on the magnetization. So here we are going to play a game which in a sense is a bit similar, but has a key difference. So basically we are going to transform the Ising model into some other Ising model, which basically is also going to involve some kind of representation with edges. But the key difference here is that this new model that we are going to study, it's not equivalent to the Ising model. It's really just something that has the same partition function, but which is, well, the set of edges we are going to look at, it's not something which is related to a spin configuration. So before, the contour model, it was just a different way to look at the spin configuration. This time we will have a different model which is not directly related to the spin configuration, but it turned out that the relation between the two models is something more intricate. It's just that the two models have the same partition function. Okay, so when I'm saying this is quite abstract, so maybe we can start to work on this and try to rewrite the partition function. Okay, so we'll start with from a simple identity. So, okay, our Gibbs weight, okay, the exponential of the Hamiltonian is just a product of terms of this form. Okay, and basically we are going to want to expand this product. So in order to expand this product, you kind of have to write this in as a sum. So let me say, let me say in more details what I mean by this. So I want to say that this thing is equal to this. Okay, this is not always true that exponential beta u is equal to cos hyperbolic beta plus u sinus hyperbolic beta, but here this thing is taking values plus or minus 1. So you just have to check that this is true when this product is equal to plus 1 and this product is equal to minus 1. And then, okay, then it's kind of obvious. Okay, so, and then I'm going to want to write it. Okay, this term, I don't really care about it. What I will want to do is really an expansion of this product when I take the product over all the edges. Okay, so let us recall what our Hamiltonian is. So we are looking at the model with plus boundary condition. And for today, okay, lambda is going to be just a square box. So it's not really important that lambda is a square box. What's important is I want to make sure that on the boundary, like on the external boundary, each vertex is only linked to one vertex inside the box. Okay, and this is true for cubes. Okay, and well, there are some choices of lambda for which this is not true. Okay, it's not something super important, but it's just so that what I'm going to say next is not well. Okay, I will tell you when I'm going to use this. So this Hamiltonian, it's just beta times the sum over xy in E lambda of sigma x, sigma y, plus the boundary term, which is the sum over xy in delta lambda sigma x. Okay, and well, I'm just going to write it as sigma x times sigma y, and we are going to take the convention that sigma y is equal to plus 1 if y does not belong to lambda. Okay, just to make sure things easier to write. So this thing, I will just write it as beta times the sum over x, y in E lambda sigma x, sigma y, where E lambda, it's equal to, well, the set of edges inside the box and the set of boundary edges, the union of edges inside the box and boundary edges. Okay, so far so good. So now, when I'm looking at this, what I have, it is just, well, it's just the product over E in E lambda of exponential beta sigma E. Okay, and using this, I can just rewrite it as hyperbolic cos of beta to the power the cardinality of E lambda times the product over E in E lambda of exponential of 1 plus hyperbolic tangent of beta times sigma E. Okay, now the idea is that I'm going to expand this product. So let me write this as a lemma, but okay, it's an exercise in the book, but I don't know exactly what there is to prove about this. So this product, okay, just writing the expansion. So let me write this in this. So if you have a product over a finite set like this, you can write it as a sum over subsets of E of product over E Fe. Okay, so this is just the expansion of the product, okay? Here you have, when you expand, you have 2 to the n terms, okay? And basically, each of these 2 to the, okay, I'm saying n, 2 to the cardinality of E term, okay? And each of these terms, it corresponds to a subset of E, okay? Basically, you're taking f of E for these, for the edges in E, and you take 1 for the others, and you get exactly this. Okay, so if we do this, then we obtained that this thing is equal to this term. Then you get sum over E included in E lambda. And then we get tangent hyperbolic of beta to the power E times the product over E in E of sigma E. Okay, and I think we are done here. Okay, so now the idea is we want to use this in order to have an expression for the partition function. For the is. So that then the sum of the partition function will appear as a sum over subsets of this. So then it will naturally define a model on configurations which are given by a subset of edges, okay, which are either in the box or on the boundary. Okay, so what we think here is this term does not disappear. Then you have sum over in E lambda. What I'm trying to do is to put the sum over sigma as much inside as I can. And now, okay, so now if you take some E, well, this defines a graph. Okay, so we are going to look at GE, okay, which is a graph which has as a set of vertices lambda union the external boundary, and as a set of edges E. And I'm going to call dE of x, it simply is a degree of x in G. Okay, so the number of edges that are adjacent to x. Okay, so now if you look at this here, well, here you have spins for vertices in the boundaries that appears, but they don't matter because they are all equal to +1, so you can just ignore them. But then if you look at, for some x in the box, if you look at the number of times that the factor sigma x appears, it's exactly dEx. Okay? Well, it appears once per edge that is adjacent to x. Okay, so therefore, the sum over sigma in omega lambda of product of E in E of sigma E, well, this thing, okay, so if all the if all the degrees are even, then you always have sigma x to an even power, which is always equal to 1. So this whole product is equal to 1, okay, for every configuration sigma. So therefore, the sum is just equal to the number of configurations. Okay, now if for some x, so this is if all dEx are even. Okay, now if for some x the degree is odd, okay, then in this product, okay, basically you have, I mean, this thing is just equal to sigma x times the product over okay, because sigma, I mean, if dEx is odd, sigma x to the dEx is just the same as sigma x. Okay, and then you sum over the two possible values of sigma x, which are +1 and -1, and you get 0. Okay, I mean, this thing, it's the same thing as summing over the product over x in lambda as the sum over sigma x in +1, -1. Okay, and basically you only need one of the, I mean, then this thing is factorizing. You only need one of the sums to be 0, and if you have just one vertex with odd degree, this gives you this 0 sum. Okay, you have +1 plus -1 is equal to 0. Everybody agrees with that? Okay, so let me just write it fully. Okay. What we have is that sum over sigma in omega lambda of the product over E x in lambda of sigma x to the dx. Okay, this is equal to No, 2 is the size of is the size of the box. This is okay. This thing, it's just the cardinality of omega lambda. No. Okay. Okay, so what I'm claiming is that this is equal to the product over x in lambda of the sum over sigma x in plus minus 1 of sigma x to the dEx. Okay, and this thing is equal to 0 if dEx is odd. Okay, so, and this is equal to 2 if it's even. So basically, if all the degrees are even, all the terms, these terms are equal to 2, so you get 2 to the power lambda. Okay. So this is the file. Okay, so then we can rewrite our partition function, and we get the following. So we define E lambda even to be the set of E in E lambda such that for all x in omega, for all x in lambda, dEx is even. Okay? And what we have is that then lambda beta plus, it's equal to, so you have several prefactors. So cos hyperbolic beta to the E lambda 2 to the lambda, and then that's it. Sum over E in E lambda even okay, so I mean, basically, now with this, okay, you could define basically an associated model, which would be you could define U, which is just divided by something, okay, divided by the sum. Okay. So the state space would be this, so the set of configuration for which the degrees is even for every x inside the box. And the probability of a configuration would be proportional to tangent hyperbolic of beta to the power e. Okay, and basically this model would have as a renormalizing factor exactly this sum. So I mean, like, apart from this constant in front, it has the same partition function as our original model. Okay, so we are not going exactly to have to study this model to have information about the magnetization, but in fact, really, the information we will get about the magnetization is really related to the typical behavior of this model. So I will have to talk back about this at the end of the lecture. Okay, so now we have rewritten the partition function. What we really want to estimate is the magnetization at 0. And the magnetization at 0, it's just the quotient of two things. One of the denominator is a partition function, and the numerator is something that looks very much like the partition function. So what we are going to do now is basically apply the same treatment to the numerator and see what we get. Okay. So let me write what is sigma 0 lambda beta plus times z beta lambda beta plus. So this thing is just the sum over sigma in omega lambda of sigma 0 exponential h beta h lambda beta plus sigma. Okay, so, I mean, basically, we have exactly the same thing except that we have a sigma 0 in front. Okay, so I can just do exactly the same thing as I've done before, except that okay. How much should I, so. Okay, so. Okay, so right now I'm not doing so much. Okay, I'm just saying that if I want to rewrite sigma 0 times the exponential of the Hamiltonian, I just have to multiply by sigma 0 at the end. Okay, and when I'm doing this, basically, what I'm doing in this product, so just multiply by sigma 0 lambda beta plus here. What I'm doing in this product is I'm just adding plus the indicator that x is equal to 0. I mean, it's just this product times sigma 0. So it's just that when x is equal to 0, I just add 1 in the power. Okay? So now when I sum, I have to wonder whether the sum cancels out or not. And so let me write this here. So the sum over x over sigma in omega lambda of the product over x in lambda of sigma x to the dex plus indicator x is equal to 0. Well, this thing, exactly for the same reasons as before, I mean, basically you want all these things to be even for the sum to be non-zero. And when it's non-zero, it's equal to 2 to the lambda. So what this means that this thing is equal to 0 if either there exists lambda x in lambda minus 0 such that dex is odd, or de0 is even, and this is equal to 2 to the power lambda if this doesn't occur. So if for all x in lambda 0, lambda minus 0, dex is even, and dex is odd. D0 is odd, sorry. Okay, so so let me call this pink star, and what we have is that pink star, it's equal to, okay, so all these things, all the prefactors are the same. And then you have the sum over E in E lambda 0. Let me just check my notes that I'm using the same notation that I decided for. Yes? So I mean, it's just the same thing as before. The only thing that differs is the set of configuration on which we are summing. So now this E lambda 0 is simply the set of E included in E lambda such that dex is even for x in lambda minus x and minus 0 and odd for x equals 0. So far, so good? Okay, so what I will do now is just draw a configuration in this, and to try to guess what we should do. Okay, so if you remember when we did the large temperature, the low temperature case, a large beta case, really what we had to show was that in the numerator, basically, all the, basically you could show that the numerator was much smaller than the denominator by factorizing something. This was the idea. So we are going to do something similar, and maybe this will help to visualize what we should do. So here is my box. So here, this thing will be the boundary of lambda. So if you want the vertices in lambda, they are the ones that are here. Okay, and so if you want to draw a configuration, basically, what you have, you want to make sure that you draw a graph where everything has an even degree, except that you remember that you don't care at all on what happened on the boundary. And in fact, on the boundary, when you have an edge, the degree has to be 1 because these guys are they just have one adjacent edge. Okay, and then you realize, okay, so let's say that 0 has degree 3, for instance. And if you look at the connected component of 0, it has to be attached to the boundary. The reason why is that if it's not attached to the boundary, then if you look at the sum of the degrees on the component, it would be odd. Okay? Because it would have 0, which has an even odd degree, and all other vertices would be in lambda, so they would have even degrees. So the sum of the degrees would be odd, and the sum of the degrees is just twice the number of edges, so it's never odd. So the only way out is you have to be connected to the boundary because the boundary gives you access to odd degrees. So let me make sure that I don't. Okay, so basically you have this connected component, and you can look at all the rest, which are. Okay, this is not. Yes, this is true. It's fine. This has degree 3, I guess, and this has also degree 3, so this is not good. Okay, I should have. I started very well, and now so this is not. This is fine. Up. Yes. Okay. Yes. So I think. So let's imagine that this is a configuration. Okay, I think everything has to. Okay. Yeah, it's not quite all right. Yes. Oh, this one. Okay, so what I wanted to make visible on this picture is that. So you know that the connected component of 0 is connected to the boundary. And the other thing which is clear is that once you take away this component, what you get is a graph for which all the degrees are even for vertices in lambda. Okay, so let me formalize this. So I will define okay, let me. Okay, so okay, for E in this, I will just want to write E is equal to E0 union E prime, where this is the connected component of 0. Okay, so what we have seen is that this thing has to touch the boundary. So what we have is that V of E0, which is equal to the union over E in E0 of E, contains 0. Okay, so now I just have to describe the space in which E0 lives. Okay, so it's just the set of configuration which induce a connected graph. Okay, so V of E is a set of vertices adjacent to E. Okay. So VEE is just the graph which, just contains which is induced on the vertices that touch some of the edges. Okay, and I'm just going to. So what we have is that we have a unique decomposition E into E0 and E prime, where E0 belongs to E0 con, and E prime belongs to E lambda even. Okay, so the second thing is is simple because E prime is just E minus the connected component of 0. Okay, or minus the set of edges that are in the connected component of 0. And if you look now at this thing, well, this is equal to 0 if x belongs to V of E0. Okay, by definition, we have taken away all the edges in the connected component. Well, we have taken away all the edges of E0. And because E0 is defined as the connected component of 0, the other edges that are adjacent to these vertices, they cannot be in E. And it's equal to dE of x if x belongs to lambda minus V E0. Okay? And this is even, okay? Because this set does not contain 0 by definition. Okay, so this is just to justify that E prime is in this set. So therefore, you have this decomposition into of if you have a configuration in E lambda 0, you can decompose it into a configuration of E lambda even and some connected component of 0. Okay, so we are almost ready to conclude. So now what we have is that sigma 0 okay, just let me think about this sum, okay? So we want to bound, to bound this sum from above. Okay, so what I'm saying is that this sum it's equal to, okay, so here I have to be a bit careful. So I want to write an inequality, okay, just so, I mean, of course, this transformation here, it's injective. Okay, I mean, really, if I give you this, you really can find back the original configuration just by but it's not completely surjective, okay? You have to add some condition on these two things for them to be really the decomposition of E. And the only condition is that the set of vertices adjacent to E0 and adjacent to E prime, they have to be distinct. Okay, so this thing is equal to the sum over E0 in E lambda 0 con, the sum over E prime in E lambda even of and then I have to put the indicator that V E0 and V E prime are disjoint. Okay, where Okay, VE is just okay, the union of the edges, so the set of vertices that are adjacent to at least one edge. Okay, so I'm just interested in upper bounds, so I can just drop this condition, and now I have a product that factorizes, and now when I take the quotient, these things will simplify. Okay, but I think before having the inequality, it's nice to know what the equality here is, what you're losing here. Okay, so all the conclusion of this, I mean, like when you take the quotient, this simplifies as well, and only this sum here survives. Okay, so here's the tangent hyperbolic beta to the E prime, okay, will simplify, okay, and only this. So what we get is that okay. Sigma 0, lambda beta plus, it's smaller than the sum over E lambda 0 con okay. So now to conclude, okay, I have to get a bound on this sum. And well, the first observation is that any E0 that appears on this sum has at least n edges, okay? So remember, lambda n is minus n to the d. Okay, so if you want to reach the boundary, you need at least, in fact, n plus 1 edges. Okay? So let's be rough, but not too rough. So, okay, this restriction on the degrees, I mean, okay, so let me write something, and then I will define the terms later. So this is smaller than the sum over n larger than n plus 1 of Cn tangent hyperbolic beta to the power n. So now basically n is, okay, so okay, I want to say this is smaller. So n is the number of edges I have in E0. Okay, and I know that it's larger than n plus 1. Okay, so if I wanted to have an equality, basically Cn would be the number of choices for E0 with n edges. But maybe this is difficult to count. And also when you write things in this way, it's kind of clear that the only thing you need is you want Cn. I mean, our aim is to prove that this goes to 0 when big N goes to infinity. For this to go to 0, you just need to make sure that Cn does not grow more than exponentially fast. Because if it grows exponentially fast, okay, you just need to take beta small to counter that. So this thing will be exponentially small in n, and therefore the sum, I mean, the full sum is summable, so the tail goes to 0. Okay, so for Cn, we just need an upper bound for the number of E0s with cardinality n, and therefore we'll just take Cn to be the number of connected subgraphs of ZD which contains 0. Okay, the idea is that, well, okay, the restriction that we have to stay in the box is not really important because when the box goes to infinity, you don't really see it. The restriction on the degrees, it probably makes the combinatorics problem much more difficult, and we are not looking for a sharp bound on beta critical. So, okay, so what we are going to prove, and this will be sufficient to conclude. Okay, and yes, so what we are going to prove is that Cn is smaller than 2d to z2n. For all n larger than 0, I guess. Okay, so this is lemma 1. So how lemma 1 allows us to conclude? Well, what we have is that if tangent hyperbolic of beta is smaller than 1 over 2d to the 2, then sigma 0 lambda n beta plus, okay, maybe I should put n here. It's smaller than the sum over n larger than n plus 1 of 1 over 2d to the 2n tangent hyperbolic beta, and this goes to 0. Okay, just because this is a geometric sequence whose parameter is smaller than 1. Okay, and I mean, somehow you get, I mean, from here you get this kind of general intuition that in statistical mechanics, when thing goes to 0, very often they have to go to 0 exponentially fast. Okay, so now let's prove the lemma, and to prove the lemma, we are going to prove, to use actually another lemma. So if VE is a finite graph, a finite connected graph, sorry, and x0 belongs to V, there exists a path of length 2n, well, 2e that use each of the graph exactly twice. Okay, so just a comment here. This inequality here is, okay, I think this Cn, it grows exponentially, but 2d to the 2n, I don't think it's anywhere close to a sharp bound on the way it grows, but here we don't really care about overcounting. And okay, in many instances, it's just the case. You just need a bound. You do not need it to be sharp, okay, for things to work. Okay, so let me explain why lemma 2 implies lemma 1, and then we will prove lemma 2. So why does lemma 2 implies lemma 1? Okay, so well, lemma 2 for each of this graph gives you a lattice path. Okay, and this transformation has to be injective because when you have the lattice path, you have the set of edges in your graph. Okay, they are just the set of edges that are used by the path. So therefore, I mean, two graphs have to give you different paths. Okay, so basically what this tells you is that if you count the number of paths of length 2n, well, you're counting more than connected subgraphs. Okay? I mean, basically because there will be some paths that don't encode graphs, and there will be paths that encode the same graph, but basically, yes. What's important is that one path can correspond to only one graph. Okay, so when there is some assumption in the, so there exists the lemma is that there exists a path of a length 2e starting from x0. Okay, and we are applying this with x0 being equal to the origin of ZD. Okay, and yeah, and now you know very well that this thing is smaller than, well, you have 2D choice for each step, so you get 2D to the n. Okay, so now let us prove lemma 2. And yeah, if you want, there is a proof by induction in the book. I'm going to present you a different proof, which is, okay, which is more geometric, it might be a bit more complicated to write, but it has the advantage of giving you really the way to find this path. So, okay, and what's the idea of the proof here is that the starting point is that, okay, I mean, these are basically two steps. So basically, if your graph is a tree, there is kind of a natural choice for choosing such a path. And if your graph is not a tree, maybe you can make it a tree. Okay, so the way we're going to make the graph a tree is not the usual way. But it's also a natural way. So. Okay, so I'm going to use the following geometric properties of tree, which is that you can embed them in a half plane. Okay, so if VE is a tree, so a graph without cycles, then, okay, I can draw it in the half plane. R times R plus, and placing x0 at the origin. Okay, so when I mean that I can draw it, I just say that I can just draw all the edges in a way that doesn't cross. Okay. I think everybody is going to accept this fact, and once you have this, the way to draw your path will just be to go around the tree. So you start from the left of the x0, okay, and you just go around the tree. Okay, and I mean, let's not try to prove this, but if you do this, you're just using the edges twice, okay? Just because you visit them once on the left and once on the right. Okay, so this is a proof when your graph is a tree. Now, when do you do when your graph is not a tree? So I don't know if you've already been trying to fix this fact that some graphs are not tree. Usually what you do, okay, what we did in the percolation course was to, well, if there was a cycle in our graph, we would just delete an edge in that cycle and then iterate until we get a tree. And of course, this is a really bad idea here because if you delete edges, you're changing the number of edges, and the number of edges plays a crucial role in your result. So this is not what you want to do. Okay, but let me just draw a graph which is not a tree. So I don't know, this thing. And basically, another way to make it, what we can do is that each time you meet a cycle, what you can do is just cut the graph just at a point. Okay, so the idea is just to make a tree, I will just cut it here. Okay, let me. There. And just. There. Okay, how many? Do I still have cycles? Yes. Okay, so let's. I have to visualize the thing. And okay, and there. So I just, delete a very small portion of the edge, and this make my thing a tree, and then I can just okay, here is 0, and I can just go around it, and I have my path, so I'm happy. Okay, so what I'm doing is instead, when I have a cycle, instead of deleting the edge, I'm just keeping the edge. I'm just taking it away from one of its extremities, okay, and I'm create a new vertex. Okay, so let's write just formally what I'm doing. And what's important, let's write how we can recover the path. I mean, here it's kind of clear on the drawing how the path is drawn in the original graph. But let me okay. Just make an effort to do it, to write it in a clean manner, okay? So, okay, so here is procedure to make a tree out of V. Okay, so okay, so what we are doing is we pick an edge which is in a cycle, we erase it, but then we don't stop there. We add a new vertex, okay? And we add an edge which is linked, which links one of the vertex of E to this new added vertex. Okay, so this newly added vertex is just my orange cross. Okay, and the idea is that this vertex y prime, it's supposed to replace y. Okay, so y is just a vertex which is not x. And so I will call y the ancestor of y prime. Okay, and I just iterate this thing. Okay, and I get a new graph, okay, which has no cycles because you see, basically each time I do this, I just, I reduce, I keep the number of edges constant and I add, I increase the number of vertices. So at some point, I will have enough vertices to make sure that I have a tree. Okay, I'm not changing connectedness by this operation. Okay, so this operation does not affect connectivity or connectedness of the graph. It increases the number of vertices while keeping the number of edges constant. So I don't know, I think in a tree, basically, the number of vertices is just a number of edges plus one. So once you've done this enough time, a tree is going to appear. Okay, so then what you get is a graph which is V prime, E prime. And what's important is that V prime, it's V union a bunch of people. What's important here is that all these people, they have an ancestor which is in V. So, okay, here maybe that's the important point. When you create an ancestor, it's a leaf of your graph, and it's going to remain a leaf forever. So, for instance, a newly created vertex, it can never be an ancestor in the future, and this is an important point. So now, basically, what's important is you have a natural projection from V prime to V, which to X associate X bar, which is either X if X is in V, or the ancestor of X if X is not in V. Okay, so. Okay, and now, if you look at, I don't know, pass yi I equals 0 to 2n, that start from x0, well, so that will pass in V prime, E prime, such that y0 equal y2n equal is equal to x0, okay, then I equal 1 to 2n is a path in VE that use every edge twice. Okay, so basically what I mean, I'm doing nothing more than what I did on my drawing, but basically what I'm saying is that once I'm using the fact that V prime is a tree to define a path that does the contour. And now what I'm doing is I'm projecting on the original graph, which is just that I'm identifying each of these newly created vertices to where they came from. Okay, and I mean, basically you have to, the fact that it uses every edge twice, yeah, I mean, basically, both the fact that it's a lattice path and the fact that it uses every edge twice is just the fact that the edges in E prime and in E, they are really in correspondence, just by construction. Okay, so I think this proof, when you try to start to explain, it's harder to explain than the proof by induction, but in a sense, it gives you the construction of the path, and it's a quite natural one. So. And so this concludes the proof, and okay, this leaves us some time for a bit of digression. So. Okay, so what I want to talk about now is a bit about dimension 2. So I've done all the pictures in dimension 2, but of course, what I've said is valid in any dimension, and it's something which is different from what we did for large temperature. Okay, here's the picture I drew. I mean, you can really generalize it in any dimension you want, and you won't have plaquettes or anything. You still have edges. Okay, but okay. Okay. So the first comment I can make is that maybe we can improve a little bit. So, I mean, remember there is a beta critical that separates supercritical phase and a subcritical one. Okay, and what we have proved so far, okay, so I didn't even bother to write a bound in the large temperature case, but what we have proved today is that this thing is let's see. Yes, larger or equal to 1 over 2d to the 2. Okay, so beta c is larger than the inverse of hyperbolic tangent of 1 over 2d to the 2. So, okay, so in d equal to, okay, this is equal to 1 over 16th. Okay, so just not modifying so much to the argument, you can go down from 16 to 3. So would anybody have an idea of how you would do this? It's just counting something that are simpler than connected graphs, and on which you would have a larger bound. Okay, so what's the kind of objects you can count which has cardinality smaller than 3n? Well, self-avoiding walks, or at least walks that don't go back on their track. Okay, okay, so how do these things appear? Well, when we did our separation, E gives E0 union E prime. Okay, we did things a bit roughly by considering connected components. What we could have done, because we're in 2 dimensions, is say, okay, we just apply our separation rule, okay? And what we have is not exactly a contour configuration, but we would have something like this. So, because basically you have these things of degree 1 on the boundary that kind of helps you. So you don't have to close the contours if you start. But you would have things like that. So, and then you would have a pass at 0, and this pass would have to end on the boundary. You can't do a closed loop if you have one extremity. Okay, and I mean, I leave this as an exercise, but if you do, basically, if you say, okay, if you see E as a set of loops like this, so if you if you do the decomposition, basically you apply this rule, and then you take away the connected component with a new connectivity rule. Okay, then when you take away, it really has to be a path, okay, because you have no vertices of degree 4 anymore. All the vertices are of degree 2 or 0 or 1 if they are on the boundary or if they are 0. And then you can make basically the same operation as we did. Okay, and then when you're summing over all the possible paths linking 0 to the boundary, well, you know that you have at most 3 to the n of them, and you get that your sum converge if tangent hyperbolic beta is smaller than 1/3. So kind of a big improvement at the cost of basically having a result only in dimension 2 instead of having something completely general. And remember that here, I mean, the monotonicity goes in the wrong way, so it's really important to prove something for every D. Okay, because the magnetization, it's increasing in D. Okay, so if you prove that it's 0 in dimension 2, it doesn't tell you anything for higher dimensions. Okay, so this is the first comment. And now this brings down, well, okay, if we can do better than, if we can go from 1/16 to 1/3, I mean, this was a big improvement for cheap. Maybe we can try to figure out what's the true value of beta C. Okay, we won't do this, but maybe we can try to guess what the value should be. And for this, maybe we can recall an analogy for with percolation. So in percolation, the critical value for P was the value of P for which percolation and dual percolation were the same process. So here the idea is that we want to consider that, well, the Ising model is really a contour model in dimension 2. And this thing is kind of a dual contour model in a sense, okay? And that the critical parameter, the critical beta, should be the one for which these two models are the same. Okay, so let me maybe be a bit more specific about what I mean by these models are the same, and yes, so, okay. So, okay, so this is not exactly the contour model we've seen last time. Okay, for several reasons. So the first thing is that, yeah, there is this special thing at 0. But this special thing at 0 It's only because here we are looking at the expectation of sigma 0. But if you look at the pure partition function, you don't have this. Okay? But on the other hand, you have these things. On top of contours, you have lines going from the boundary to the boundary. Okay? But in fact, these lines, they don't necessarily have to appear. It really depends on the kind of boundary condition you choose to observe. So if we did the same operation as before, but looking at z lambda 0 beta, okay? I mean, just doing exactly the same thing. Here, you know, the edges you would have to consider are just the edges inside the box, okay, because you have no boundary edges. And the sum here would be, okay, I would put a bar here just to differentiate with what we had before. Okay, so here what we would E lambda even would be the set of E in E lambda such that dE of x is even for all x in lambda. Okay, and this thing, okay, if you remember, it's really similar to what we had in the large beta expansion, where we had here that okay, this was basically the sum over sigma in omega lambda of product over gamma in gamma sigma of exponential minus 2 beta gamma. But I mean, here you can just see this thing as an edge configuration where every vertex has even degree, and this is just exponential minus 2 to the beta to the power of the number of edges. Okay, so what I mean is that this thing is just the sum over E prime, okay, in E even star lambda of exponential minus 2 beta prime. Okay, I have. To the E prime. Okay, where these are edges configuration that satisfy this, but they live on the dual lattice. Okay, so basically, here, for any values of beta, I mean, we always have well, you have two ways to represent your model as a contour model. And now, I will try to convince you that maybe this would be, this can be, okay, sufficient to heuristically identify the critical value for beta. So okay, so okay, now let's not care too much about the details. I mean, we have a contour model. Each edge has a cost lambda to appear, where lambda is some parameter. Okay, I mean, in our application, lambda is always smaller than 1, but it doesn't not necessarily has to be. Okay, so what's the idea? So if beta is larger than beta c, then the magnetization is positive. And what this means is that the probability for the contour model, under the contour model, to have, under this kind of twisted contour model that appears when you compute the expectation of sigma 0, the probability of 0 being linked to the boundary does not decay to 0. Okay, so what does it tell you about your contour model? It tells you that basically, okay, so what I expect here is that for this thing, I have a critical value for lambda, below which I have, so this is lambda smaller than lambda c, I have only small contours living in a big phi of nothing, okay? And if lambda is larger than lambda critical, then I have contours of all sides that are crazily nested into one another, okay? Like if you want digital prints. Okay, so, I mean, basically you see that if lambda is small, it's very costly to create large contours. Okay, so all your contours should be small. And when lambda passes a threshold, maybe, I mean, if lambda is smaller than 1, this costs exponentially. This is exponentially in the number of edges, but you know that the number of contours with a given length also grows exponentially. So you have this competition, and maybe when entropy wins, this is the kind of thing that start to appear. So here you have m beta. So this means that large connections occur, okay, for a model which is very related to the contour model. So this kind of tells you that tangent hyperbolic beta should be larger than lambda c. Now, if beta is smaller than beta c, then basically, I mean, you know that in a box centered around the origin, you don't really see the difference between plus boundary condition and minus boundary conditions. Meaning that the contour picture must not look like this, because if not, you would kind of, I mean, in every place you would see whether you live in an ocean of plus or an ocean of minus. Okay, so this means that lambda has to be above lambda critical. Like you are surrounded by so many contours that you don't really know the number of contours you've crossed to come to the origin. So this means that exponential minus 2 beta is larger than lambda c. And in fact, I mean, you can. I did this in one direction, but you can also do this in the other direction. Like so, what this tells you is that basically tangent hyperbolic beta is equal to tangent hyperbolic beta c is equal to lambda c, and exponential minus 2 beta c is equal to lambda c. So, what you get out of this is this. Okay, this is what should occur. And therefore, you should have beta c, which is equal to 1/2 of log 1 plus square root of 2. Okay, so of course there is no way to make this argument rigorous, and the proofs that has been achieved of this equality yeah, unfortunately, they don't. Yeah, they rely on more tricky argument than this. But this is basically one argument that that tells you that I mean, basically, criticality it must be exactly at the point where the contour models that appear in the low temperature representation and the high temperature representation are the same. Okay, so some kind of self-dual point for the model. Okay, so we are going to stop here. What I will do tomorrow is go back to the case of non-zero magnetic field, okay, and prove that the free energy is analytic in H when H is not equal to 0. So basically that tells you that, I mean, not only it's differentiable, so you have uniqueness of the Gibbs states, but also if you look at the magnetization as a function of H, it's super regular in the sense that it's analytic as well. It's the derivative of an analytic function. So really the only, I mean, this will kind of complete the phase diagram in the sense that what we will have proved is exactly this thing. So this is beta, this is H, this is beta critical. And basically, if you move your parameter in anywhere in this region, well, okay, first, I mean, on any point on this region, you have uniqueness of the Gibbs state, and if you move, basically magnetization is continuous with respect to the motion you do. But if you try to cross this, then you have discontinuity of the magnetization. Okay, this is where you go from m star to minus m star. Okay, so, okay, I didn't stop a lot for questions today, so do you have questions? Okay, so the exercise list will be for, yeah, Tuesday in 2 weeks. So I guess, okay, what day are we today? So tomorrow is 1st of March. So I guess it's 14th of March. 14th of March until 23:59.